Good afternoon, everyone. I want to thank you for coming for today's seminar. I'm Dong Chen, an assistant professor in FIU ICIS. So today it is my pleasure to introduce to you our invited speaker, Dr. Fei Miao from UConn. So Dr. Fei Miao is an assistant professor in the Department of Computer Science and Engineering, and she is also affiliated to the Institute of the Advanced System Engineering, also at the University of Connecticut since 2017. Her research interest lies in the intersection of control, optimization, and machine learning with application in the several physical systems, in particular with the efficiency, safety, and security. She has received a couple of awards from NSF, including S&AS, CPS, and S and CC programs. She received her PhD degree and also the Charles Hallock and Sarah K. Wolf Award for the best doctoral dissertation in electrical and system engineering with a dual master degree in the statistics of Wilson School from the University of Pennsylvania. She received her bachelor degree majoring in automation from Shanghai Jiaotong University. She was also a postdoc researcher at the Grasp Lab and the Process Lab at UPenn from 2016 to 2017. She was a Best Paper Award finalist at the ACM at IEEE International Conference on Cyber Physical System, ICCPS 2015. So today, Dr. Fei Miao will give us a talk about her research, learning for robust control and optimization, efficiency, and safety of the autonomous transportation systems. So we will also have a short Q&A session at the end of today's talk to answer your questions. Please give a warm welcome to Dr. Fei Miao to give us the talk now. Thank you very much.
Okay. I guess it's my turn. Thank you for the introduction. And I do hope now I can physically be in the warm Miami area. Today I will be mainly talk about my research related to learning and control for robust optimization with its application in autonomous transportation systems. So most of my research lies in the field of cyber physical system. So when we talk about a CPS, usually we mean the integration of communication, computation with control of the physical world. We can see a lot of real world applications like autonomous vehicles, smart manufacturing systems, medical devices, smart grids, or building automations. So usually this is the NSF CPS program. They really like to want to use this flower to represent the core sense area and the application sectors of CPS. So for my research, I'm mainly focusing on the safety and control side and how to integrate the control with data analytics for CPS research. And today I will briefly introduce our application on autonomous vehicles, on smart transportation systems, and smart cities. So, so the first part of my talk, I would like to introduce the data-driven control and optimization I've been working on. So basically, from large-scale real-world data, we can extract information relying on machine learning methods or applied statistics methods. And usually for when we want to say we want to improve the performance of the system, from the optimization perspective, usually we mean we want to minimize some cost or maximize profit of the system. And control theory usually represent the field that how we can get from the information about the system model to actions. So with the integration of these three fields, so one very challenging example in the real world we have been working on is intelligent transportation systems. Basically, the challenge comes from the growing complexity of the system, and also the system is it's a dynamic system. it can be large scale, and the model can be uncertainty, and there can be heterogeneous data comes from different transportation modes and the different surveys. So for example, the first set of our paper comes from the motivation of ride-sharing service. Even though the revenue in taxi service and ride-sharing service has been increasing, actually, it does not mean the service are already very efficient. So basically, the shared vehicles like taxis or the Uber, Lyft, those types of vehicles, the cruising mileage can be 20 times of a private vehicle, which means they actually is the large part of all these traveling mileage in the cities. But meanwhile, if we check the idle mileage of these vehicles from a public data source, idle means the vehicles are driving on streets, maybe searching for passengers, waiting for passengers, but no passengers on it. It can be as many as 300 million miles per year. That's actually a lot of waste for both energy and also for the time of the drivers. And it causes a lot of inefficiency in the system. So before we started our data-driven optimization research, most existing work in this sort of ride-sharing field usually the demand prediction and the optimization part is relatively separated. So there have been a lot of model like time series or just using Poisson model to predict the demand and cheap inference of this ride sharing service or just a normal taxis. But meanwhile, on the other side, the optimization-based approach, the resource allocation problem, or trip scheduling solutions usually assume that we have a perfect model, a perfect knowledge of the system side, what are the dynamics of the system, or just assume, well, given the set of people's mobility demand, how we can schedule the vehicles. But in the real world, the case is, well, actually, of course, we receive real-time demand, but we do not have a good idea saying, well, I already know in the next hour or in the next 2 hours, what will be this sort of ride-sharing demand or taxi demand, right? So the novelty of our work is basically we bring data-driven, robust optimization to improve the system efficiency for this kind of a ride-sharing service. So we mainly tackle about the unbalanced and inefficient ride-sharing service. Say, well, some places might have a high demand and the peak already appear, but not enough vehicles to serve it yet. Or maybe there are in some rural area there is demand, but vehicles will seldom go to regions like that. So basically, the scenario is there is no system level optimal and proactive balance according to the predicted demand. And we would like to tackle this issue. So we assume that our first set of approach is centralized based approach. We assume that there is a dispatch center can collect data, both historical data and the real-time vehicle mobility data, and know the current status of the vehicles in the entire system, whether it is occupied already or it is an idle vehicle. And we can collect the pickup and the drop-off event data from all the vehicles. So the dispatch center, so we will predict the future demand of the passengers, and considering both predicted future demand and also the current unserved demand to basically dynamically update our control decision, what we call real-time control decision, to make sure that we reach some optimization objective. And then the interesting part or the challenge part, considering the scale of the problem and the uncertainty of the model includes, for example, we have limited resource. but we might have a lot of demand we need to serve. And there can also be conflict of interest on the customer side and the system side, right? So customer just care about, I mean, as an individual customer, I just care about to reach my destination as fast as possible. But from the system level, instead of just focusing on each individual customer's benefit, we also need to think about, well, for the entire system, can we basically, for example, minimize the total idle mileage of all the vehicles while we can serve those customers, right? So then basically on the system level, what we do is the system will predict the demand and will do a robust resource allocation to balance demand supply ratio for different regions across the entire city. And meanwhile, we want to make sure that we reach this sort of balance and fair service with minimum idle driving distance. And it can be hierarchical approach, and there can also be local controller run either heuristic, greedy, or carpool algorithms to advance specifically like which vehicle will pick up which passenger. So I will first talk about the basic optimization formulation of the problem, and then we will see how we deal with the uncertainty of the model. So first, from the centralized controller perspective, we divided the entire region, the entire city to maybe several hundred regions according to the city map, and we have spatial temporal data, right? So basically, the demand and the locations of vehicles, they dynamically change, and that's spatial temporal data. So the centralized controller usually updates the control decision every 30 minutes or per hour. So basically, we use the spatial temporal data to predict the demand and mobility pattern. Here we mean, when we say predict the demand, we mean on this system level, for example, at the next 3 or 4 hours, what are the predicted total demand at each region of the city? And the mobility pattern is also on the city level saying, well, for what percent, for maybe for like a for 30% of vehicles starting the trip in this region will end up its trip in its adjacent region within the next hour, etc. So this sort of level of mobility pattern. And then the major contribution of the major algorithm part will do this dynamically optimize. So when we optimize our decision, we consider both serving the current already like appeared demand in the system and considering possible future demand at different locations of the city. So we want to make sure that our balanced decision basically in the next few hours, this balanced decision can be really efficient according to predicted future demand of the city. We don't want to say, well, at the next hour, we send a lot of cars to region A, but then at time t+1, we will need to send these cars again to a really far away region B. That won't be very efficient for the system. Still, we want to make sure that we are considering, well, several continuous sequence of time steps. We want to make sure the system is efficient. So, and then balance the supply demand ratio. So here are the main objective function for the optimization based approach. So the first part is about demand supply ratio. Basically, we have local supply demand ratio, and we also have global supply demand ratio. We want to make sure that these two ratios are really close. We want to minimize the difference. So, so then the second part of objective is idle distance. So basically, this is just a linear function of our dispatch decision. So the dispatch decision is basically the number of empty or vacant vehicles we will send from region I to region J at time K. So then the entire optimization problem can be written as this sort of actually if we relax the constraint of the number of vehicles to a non-negative number instead of integer, basically this will be a convex optimization problem that we have two weighted sum objectives. One is about, well, we want to minimize the total idle mileage caused by the dispatching. And we also want to make sure that the difference between local demand supply ratio and the global or the city level demand supply ratio is minimized. And those constraints represent like, well, the mobility pattern, and also like after dispatching, the total number of empty or weakened vehicles at each region should still be positive. And of course, we have mileage constraints, right? So if we want to reallocating the vehicle, we must make sure, well, the vehicle can reach can really drive from region I to region J within maybe 10 or 20 minutes, according to the current transportation, according to the current traffic conditions. So this upper mileage M, we can adjust the parameter according to our information about the traffic conditions. So basically during congestion hour, this threshold will be lower, so it can only it can drive slowly, maybe only to a very nearby region. But if it's not that busy hour, so the threshold can be relaxed a little bit. So it may be drive to further away places, so etc. So in general, this can be a convex optimization problem, and we can solve the solution in polynomial time. So for example, if we have several hundreds of regions in the city, so then basically we can find out the solution in several minutes with either MATLAB or Python toolbox. So, and we first run our experiments according to a real data set from San Francisco 1 month data set, and we found out that with this sort of vehicle balancing, compared with the historical data, we can reduce the idle mileage by about 40%. And also we can reduce the difference of demand supply ratio across regions compared with the global level. So this horizontal line is basically the city's demand supply ratio. And we can see that with our algorithm, most regions' supply demand ratio are getting closer to the city level. But it's interesting that still we can find out some regions, this kind of balancing result is not good enough. And we found out that because, especially when we doing this balancing according to our predicted demand, we still have some demand prediction error. So if we balancing towards this not 100% accurate predictions, of course, the balancing performance will not be really perfect. So this basically tells us that we should not ignore the demand prediction error or the model prediction error. So then the question is, okay, so if we have data, and so if somehow we can find out the possible range of the prediction error, then how can we deal with it? So robust optimization in the literature has disadvantages like a high computationally complexity, or it can be, sometimes it might be too conservative. So can really overcome those disadvantages of robust optimization for designing our algorithm. So then I will talk about how we design basically computationally tractable robust optimization and what we call distributionally robust optimization method to overcome these disadvantages for the traditional robust optimization method. So here, still, the first step is we need to model the uncertainty of our prediction from data. So again, still we have spatial-temporal data, and we partition the city map to regions. So the regions do not need to be this grid partition. Actually, we also try like different partition method we will talk about in the experiment part. So again, still we want to predict what is the aggregated like total number of demand in this specific region in the next few hours. So for example, the prediction method can be a vector time series. It can be, we just assume the demand arrived at each region is Poisson distribution to find out the parameter. Or we can also use like the recent very hot LSTM neural network based method. So no matter what method we use, we just assume, well, the real demand is our prediction plus some error. And we can use what is called the bootstrapped method in statistics literature. Basically, that's repeated experiments. And we can find out the confidence region of the prediction error and using the mean covariance information of this prediction error to build what we called an uncertainty sets. Basically, the uncertainty sets describe the possible range of the probability distribution of this error. And the major requirement about this uncertainty sets is it needs to be a closed and convex set. So, for example, the simplest format of the uncertainty set can be what we call just a box. Basically, it just gives a lower and upper bound of the error of prediction for each region at each time. Or it can be, for example, this Gaussian format. So of course, in n-dimensional prediction, it will be multivariate Gaussian, etc. So then with this sort of Gaussian distribution, it will include both mean and covariance information. And our optimization problem formulation also needs to change according to the prediction error. So for example, here, instead of saying, well, our predicted demand is just a deterministic value, we say, well, it can be a vector that any vector just belongs to this closed and convex set, and this set is built from data. So the decision variable is still the number of vacant vehicles we will send from region I to region J at time k. And all those constraints in the optimization functions can still be represented by basically a linear function of the decision variable and our predicted parameter. So one challenging part in our objective is this absolute value function. So remember that when we say, well, our predicted demand is a deterministic value, we say we want to minimize the difference between local demand supply ratio and the global demand supply ratio. So that's a function with absolute with this absolute value format. But the bad part of this function is this can cause very slow computation speed in robust optimization scenario. So for example, when this R as a denominator part is a vector within a set, not just a deterministic value, calculating this absolute value function that can be very slow in real world case, which we say, well, that's not computationally tractable. So the first step is we want to find out an computationally tractable approximation for this absolute value function. And we have proved that actually this new format with the predicted demand R on the numerator and the total number of supply on the denominator with a power of alpha. Alpha should be greater than 0, but it can be close to 0. Basically, the value of alpha smaller than 1 gives us a really good result. So we have proved that this new function, it's a good approximation of the absolute value function itself. It is computationally tractable. It is convex of our decision variable and concave of our uncertain parameter R. And when alpha is within 0 and 1, and alpha is close to 0, basically minimizing this new functional objective, we can get a very good result that if we minimize this new function, this approximated function, we check the result, plug in the result to this absolute value function, we find out that, well, the result is very close to 0 if we do not have any other constraints. Means minimizing this functional format, this fractional format of function is a good approximation of minimizing this demand-supply ratio difference. So the first step is we want to find out an approximation function that is convex of the decision variable and concave of the uncertain parameter. And the other parts are good. We do not need to change it. So then the original meaning of robust optimization is actually it's providing what we call probabilistic guarantee. Means that if we say, well, we have uncertain parameter that can be within this uncertainty set, then basically by solving the right side min-max problem, we can guarantee that the left set problem is always true, it always holds. So basically the optimal solution of the right side min-max problem can always make sure that on the left side problem, when we minimize the same objective function with a certain probability that the constraints can hold. So that's why we say, well, actually solving this robust optimization problem, we can provide probabilistic guarantees for the worst case cost of our solutions. And then we prove theorems that basically the min-max problem, we can find out an equivalent convex optimization format. Means, well, originally it's a min-max problem. We can prove what is the exactly minimize problem we are solving and to find out the solutions. So as we already showed, well, first step, we approximate the objective function from the original absolute value format to the fractional function format. And then according to the uncertainty set format, if it's a box type of uncertainty set, or if it's a second order cone using both the mean and the covariance information of the data, then we can prove that this min-max problem can be solved as a purely convex optimization problem, which means it has a computationally tractable form. So and then the question is, well, people sometimes criticize robust optimization. It can be conservative, right? So you just minimize the worst case cost, but for a lot of cases, we will not really like reach the worst case. So then is it possible to, for example, solving like a worst case expected cost instead? And then we find out, well, we can have different ways to describe the model uncertainties. So like in robust optimization, we see, well, this predicted demand, it can be any vector within this closed and convex set. But we can also say, well, we can describe the possible probability distribution of this random variable. So if we consider this predicted demand as a random variable, we can say, well, we assume this random variable belongs to some probability distribution, but though we do not know the true probability distribution, we can say, well, we can use a set F to describe what are the possibilities for these probability functions. And then we can say, well, actually, this time we will have a stochastic programming problem then. So a normal form of a stochastic programming usually minimize the expected cost when they know the, for example, the true probability distribution for the parameter. But with data, we do not know the true probability distribution. We know a possible set where this true probability distribution can be within. So then the problem we want to solve is called distribution robust optimization, or DRO, means that we can minimize the worst case expected cost if we can quantify the probability distribution functions range. So again, we proved the theorems saying, well, for this right-hand side DRO optimization problem, we can prove that we can find out equivalent convex optimization format, a computationally tractable form, that when this set F is described as some ellipsoid function format, and we can find out the solution still in real time. So if you are interested in about the detailed mathematical format of these optimization problems and the proof process, so we have everything published online in our paper, so you can check the detail. But the basic idea here is, originally, no matter robust optimization or DRO problem, they are not computationally tractable. And then we prove that the min-max problem can be some really nice format of minimized problem when some specific conditions are satisfied. For specific format of uncertainty set, for specific format of uncertainty set delta, and for specific format of uncertainty set F. So in robust optimization literature, usually if the uncertainty set or the uncertainty set for probability functions are second order, so ellipsoid second order cone, usually there is still method to find out a computationally tractable form. But if it's higher order, like a third order, fourth order, then I think still it's very challenging, even you have a very simple format of optimization problem. So then basically the type of optimization problem we have will be the objective function is some format of it can be a weighted sum of objectives with a linear function of the decision variable, and this fractional format of objective function, including both our decision variable and the uncertain parameter. And the constraints we have are all linear constraints. And then our proof can basically solve this robust and distribution robust optimization problem in polynomial time. And that this can be applied in like if we provide a ride sharing service with autonomous vehicles or with EVs, electrical vehicles, or like a bike balancing problem, or general resource allocation problem that can be described by this optimization format. And we also test our algorithm performance based on real data. So for example, here we, I think this is a public data set. It includes 4 years of New York City's taxi data. And we basically use cross-validation method, like a part of the data set is used to predict the demand and build the uncertainty sets, and the other part of the data is used to basically testing the performance of the algorithm. So we show that basically with robust optimization method, both the idle mileage distance and the demand supply ratio error can be reduced compared with not considering demand prediction error, compared with non-robust solutions, basically. And for For distribution robust optimization, similarly, we can reduce the idle mileage error, we can reduce the supply-demand ratio error compared with non-robust solutions. And we also compare the DRO, distribution robust solution, with robust solution, because usually robust optimization method, it does not have a good performance if you compare like the average cost of or the average performance of the solution. In our robust optimization problem, actually we can select basically the probability guarantee of cost. So actually the average performance of the robust solution is related to the probabilistic guarantee we want to reach. So basically we can find out, well, at some specific probabilistic guarantee, the robust optimization solution, the average cost is very close to the distribution robust optimization. But if the probabilistic guarantee is a very large value or very small value, the performance will not be very good. So if epsilon is large, means 1 minus epsilon is small, means, well, the probabilistic guarantee is small, means actually the algorithm is not robust. If epsilon is small, means 1 minus epsilon is large. The probabilistic guarantee is large, means, well, the algorithm is too conservative. So the average performance is not good either. So that's basically the interpretation of the property of a robust algorithm. And we also tried like different region partition method, because only using grid partition on the map, that may lose a lot of information. So actually, we found out that if we use what is called quad tree partition, basically it utilizes information based on the dynamic change of the pick up and drop off events appear at different region at a different time. And then if the region partition algorithm is better, with the same optimization algorithm, we can always improve the performance by reducing the total idle mileage and also reducing the demand supply ratio mismatch between regions to the global level. So, so based on what we have done, how we deal with uncertainty on the demand prediction side, so our current, this project just started last year. So our current CPS project, so this project is focusing on electrical vehicles data. So EV is special compared with traditional vehicles that for traditional vehicle, we can say basically the supply side is relatively stable. So the vehicles won't need too much time to refuel, right? But EVs are special that the supply side is also not that stable. So the vehicles might need to leave the service system for 30 minutes or even 1 hour if there is a long queue and the vehicle needs to wait for charging. So this makes it even more challenging when we schedule the passenger pickup algorithm, considering both, well, if some vehicles need to be charged, we need to schedule both charging and the passenger picking up events or picking up actions. So the control side is more challenging. And also the algorithm, the model prediction side, model prediction based on data is more challenging. Here we need to consider both the demand uncertainty and the supply uncertainty. So it's, with more uncertainty means, well, with more uncertainty parameters in the optimization function, and they can make the problem, especially like a large scale optimization problem, more challenging to be solved. And our CPS project will mainly focusing on these sort of challenges for EVs. And here the EVs can be heterogeneous EV, can be taxi, e-bus, or shared vehicles or trucks. So for this sort of project, it's work with my students, and we already have our first paper published in this year's IROS. So I think it's just online with a talk and a paper with a presentation video online in October. So in that paper, the first time we deal with both demand side and supply side uncertainties, and we show the proof that how we can solve that sort of optimization problem in polynomial time. And we also explored multi-agent reinforcement learning based method and just submitted the paper. So we also have recently this CPS project just started this September. So again, it's about using data and find out good solutions to basically making the service efficient. But this time, the scope is even bigger. So we have not just transportation service, we also have like maybe like a snow removal service, or like a fire trucks, or even how to schedule traffic lights. So basically, this project is led by Rutgers University. So we use the community collaboration is with Newark City. Our team has been talking with the city, the government people about like what are the problems they care about and what kind of conflict service they can quite often meet, and what is like already collected historical data reflecting these kind of surveys in the city do you have. So the basic idea is, well, we first want to identify so we can detect the conflicts among different types of surveys, and then in the future even predict possible service conflicts. And then we want to find out, we want to design good algorithms based on optimization, game theory, and reinforcement learning that we can basically resolve these conflicts instead of each department in the city just schedule their own service. Maybe sometimes we need to optimize the service a little bit and make sure that, well, if there is some, for example, there is some emergency tasks for the fire trucks or for the police to execute, maybe other normal traffic service can in advance leave some space for these vehicles to pass by. Or in the city level, there we can also see actually like a difference among communities. Maybe some communities are very well served, but some communities are not really very well served yet, but they may need the city level to allocate more resource to those communities, etc. So there can be a lot of interesting problems here, and the SCC program really emphasized collaboration between the computer science, engineering, electrical engineering, civil engineering side, collaboration with the social science side, and also with collaboration with the community side. So a lot of issues when we just design algorithms, we won't really think about it. But if we ask the social science people, they might have different perspectives, saying, well, actually, the way you measure your algorithm performance, your service performance is not really good enough. It did not really reflect like a fire service to different communities of the city yet, etc. So we want to design algorithms that also reflect these kind of social science and community needs considerations in the future. So, and we also have a project about the learning and control for connected and autonomous vehicles. So the motivation comes from the hot development of autonomous vehicles, but now it still has issues like safety. So basically, if we only relying on single vehicles sensor information, a lot of time we do not really have good reaction to like accidents or even to traffic congestions. So for both a team of like 2 or 3 very nearby neighbors or from the system level, we want to analyze that if vehicles can share information with other vehicles with the road infrastructure, so can they improve both safety and efficiency of the system? And we have some preliminary work. For example, we assume vehicles can share their position velocity with neighbors, and we design like this sort of form method and control method based approach. Basically, the vehicles will decide when to change lane or when to keep lane with the shared information. And the basic idea is, well, if by changing lane, this vehicle can help improve the entire city's traffic flow, or if the vehicle knows maybe currently it seems, well, lane 1 is a faster lane, but actually 200 or 300 meters later, this lane actually has some congestion, then at least for now, it is not a really good approach, or it's not a good policy to change lane, etc. So the shared information can bring additional information to the ego vehicle, the car C, saying, well, I know more about what will happen in front of me in the future. And then when I make the current decision, I can be smarter. So that's the basic idea. And we show that this kind of the policy we design can improve traffic flow and from the system efficiency perspective. And meanwhile, it can also improve average driving comfort if we think about, well, the car can avoid some unnecessary lane changing behaviors that is more comfortable for the people sitting in the car. So we can improve both. And we already have this like a policy synthesis algorithm published, and multi-agent reinforcement learning based method is also submitted. So I think I will skip this part about security and resiliency of CPS. So most of this sort of research are supported by what is called DOE Sesame, and also some industry collaborators. And the basic idea is, if we know the system dynamic knowledge for cyber physical system, and besides like the traditional cyber security approaches about attack detection and resilience algorithm design, we can also utilize system dynamic knowledge to find out, well, the system has some abnormal behaviors, and then how we can adding more resiliency to the system on the control algorithm side. And we have designed like a coding algorithm for stealthy data injection attack detection, and also stochastic game if we have saying, well, there can be different types of attacks and different types of detector to the system. And of course, detector with higher detection probability might also has higher cost to the system, and then how we can switch among detectors according to our, if we assume, well, the system is playing a game with the attacker, etc. This sort of approach. And overall, my work focusing on the safety, efficiency, and the security of cyber physical systems. And I'm specifically interested in autonomous transportation systems. So the major theoretical approach we rely on include optimization, control theory, and specifically data-driven optimization and control, that we build the system model among data instead of just assuming that we know exactly the system dynamic model. So here I also summarize some current project. All these active projects, my students are actively working on these projects, and I think overall they have been doing a good job, and I hope in the future we can have more results to talk about for these current active projects. So I think I can just end my talk here, and welcome to questions.
So last chance, do we have one more question? No? So if there's no more question, I would like to suggest that we can just thank Dr. Miao again for giving us this very good talk today, and And thank you for everyone to attend this seminar. I hope we have a nice weekend. So this is going to be the end of this seminar. Yeah, thank you.
Thank you.